I think so. That moved on its own. We'll put the guy's action here. Okay. Here's z equal, hey Ted, x cubed over 3 plus x minus y squared. And like I said, this is a function from economics. I was looking around the web, finding functions of two variables that we could use to maximize or minimize. And this came up. What we're going to do is find the critical values first. Okay? We've got x defined on -2 to 2 and y the same. And let's do the partials. E to the u form. So the derivative, partial derivative with respect to x, e to the u, du dx. The derivative of this with respect to x, which is a -3x squared over 3 plus 1. The derivative of y squared is 0. Okay, that's the partial with respect to x. Partial with respect to y. E to the u form times the derivative of that exponent with respect to y, which is a -2y. We want to locate our critical values by setting the partial with respect to x equals 0 and the partial with respect to y equals 0. And when we set this equal to 0, let's see what we have. What's that? Yes, exactly right. Very nice. Exactly right. When you set that equal to 0, what happens is the exponential function never is equal to 0, like we discussed. So you set this equal to 0, 1 minus x squared equals 0, and you get x is plus or minus 1. Okay. On the other hand, when you set the partial with respect to y equals 0, you'll have this. And again, this first factor is never 0. It's only 0 when y is equal to 0. We end up with two critical points. 3?
Yeah, plus or minus of the x be 2.
Okay, 1, 0, and -1, 0. Right, where do you get a third?
Gotcha, never mind.
Okay, no problem. Okay, no problem. Those are the critical points, and that's exactly what we have with the graph, except Teddy didn't see the graph. Oh, I'll have to show it to you.
It's all right.
Oh.
We'll have to watch that informative 20-minute analyzing of the graph.
So if we had,
I'm
like
busy.
zoom in
I'm
briefly
busy
and
crying over
then nothing
here.
else.
You busy what?
I'm busy crying over here. I don't think I can.
Oh, no,
I know,
why?
The tears. Physics test.
Oh.
don't cry.
Go ahead, Leon.
So if we had multiple critical values for both x and y, our critical values would be all combinations of coordinates that those make.
It would be all those combinations that cause both the partials to be equal to 0. And these 2 points cause both partials to be equal to 0. Now, the way we've done it here, because of this function, we had x's over here and y's over here, but putting them together, we get both equal to 0.
Okay, so
if you had like multiple y values, like instead of just 0, you know what I'm saying? Like you had like 0, 2, 3, and then would you combine?
Yes, you would. You'd have to combine them as long as those points cause both partials to be 0. You'd have to do them all in all combinations.
okay, so
That is
y
true.
plus minus, so you'd have 1, 2, 1, -2, and then -1, 2, -1.
Yeah, absolutely right.
Okay.
Absolutely right. Ted, this is the graph. This is the plot of the thing. What we're doing.
Wow.
That's what we're trying to maximize and minimize, find the critical values of. And we got, you notice it's got 2 points we just found here. One point is going to be this guy here,
Yeah.
and the other point is going to be this guy over here. That's going to be we're going to find it's going to be a saddle point. So this is what we're doing right now.
The mountains in your background.
Yeah, I know. It's
Similar.
pretty cool. It is. It is. I tried to simulate those exactly. All right. So, and the test to see whether these critical points are maxes or mins, we'll take the second partial derivatives. A little bit messy, but like Dan said, it's not a big deal. So let's just do it.
Consider the source.
Here's the first partial with respect to x. Let's do the second partial with respect to x. It's a product rule. It's first times the derivative of the second plus the second times the derivative of the first. And the derivative of this with respect to x, we already know, is a negative x squared plus 1. So what happens here is this. We end up with, I'm going to factor out an e to negative x cubed over 3 plus x minus y squared. And we end up with a negative 2x plus, I'm going to write it as 1 minus x squared squared. Okay, that's this. Okay. And that's equal to e to the negative x cubed over 3 plus x minus y squared. And I'm going to multiply it out, okay? Actually,
So you're multiplying out 4.
well, I'm multiplying this thing out. I could leave it just the way it is. I'm going to multiply it out. So you got negative 2x plus 1 minus 2x squared plus x to the 4th. I probably shouldn't have done that. That's the, yes,
Question.
go ahead.
So you're finding the second derivative of x. So
Yes.
technically, it's the same thing except with the first partial. Am I correct? Where do you get that? Where do you get that from? Product.
Okay, here's the first partial with respect to x. It's up here.
Yep.
You got that?
Yep.
So the second partial with respect to x, we have to take the partial of this with respect to x. And that's a product rule. So it's first times the derivative of the second. It's this. Plus the second times the derivative of the first. Now the derivative of the first with respect to x is what we already have. It's this thing again. We already have it, so just repeat it. Okay.
Okay, so there's no u form.
Well, it's e to the u times v. I mean, that's what it is, you know. So you end up with this. That's the second partial with respect to x. Now I'm going to do the second partial with respect to y, and then we're going to do the mixed partial, and we're going to test those critical values to see if we got maxes, mins, or saddle points. And we should find one relative max and one saddle point. But that doesn't finish the problem, because we got the boundary condition where we have that e to the negative x squared curve. So we've got a few things to do, which we're not going to finish, but let's we can keep on going. All right, you ready? So now I'm going to do the second partial with respect to y. Second partial with respect to y is, again, a product rule. It's first times the derivative of the second plus the second times the derivative of the first. And again, it's just a repeat of what we just had. Okay. So we end up with e to the negative x cubed over 3 plus x minus y squared. We get a negative 2 plus 4y squared. Okay. And now we need the mixed partial.
It doesn't matter which one you start with.
Doesn't matter. Take your pick. I'm going to start with the partial with respect to x and find its partial with respect to y. But there's good news here, because the partial with respect to x, this here guy, when we take its partial with respect to y, this is just a constant. So it's going to be e to the negative x cubed over 3 plus x minus y squared times the negative x squared plus 1 times the derivative of that exponent with respect to y, which is a negative 2y. You see what I mean? Okay. Now we can test. So I've got two critical values, 1, 0. We're going to find d. D is equal to second partial with respect to x, second partial with respect to y, minus the mixed partial squared. That's D. Oh, boy. Now, D at this point. D at the point 1, 0. Second partial with respect to x at 1, 0. Let's see what we get. Okay. Here's the second partial with respect to x. We're doing this at 1, 0. So, it'll be e to the negative 1/3. I'll write it out. E to the negative 1/3. Okay. Plus 1, then you get a 0. Dan's already got it? You got this, Dan?
Yeah, I got all the values.
Oh, wow.
So you plugged it all in.
Plug it all in, and what you get for D,
Applied it.
and then for D, what do you get for D here, Dan?
Which one is this, negative one or?
This positive one.
Positive one is 4 times e to the 4/3.
That is so cool. All right, that is cool. All right, that is D. You substitute them in, evaluate it, you get D is 4e to the 4/3, which is greater than 0, which is good. What's wrong? Okay. And now what we do to see if we have a relative max or min is to check the second partial with respect to x at this point, and we end up with the second partial with respect to x at this point is, when you substitute in the 1, 0, you end up with, Dan, what do you end up with here? Put in a 1 and a 0. Put a 1, you get e to the, here, I can write it out. E to the, put a 1 in here, you get negative 1/3 plus 1 is e to the 2/3. Okay. Y is 0 times, put a 1 in here, you get negative 2 plus 1, negative 1, minus 2, negative 3 plus negative 2 is negative. Is that what you got? Negative 2e to the 2/3 on that? Oh.
I did it all in one step.
Oh, okay. All right. That tells us, because the D is greater than 0, and the second partial with respect to x is less than 0, think concave down and a relative max. Whew. We got a relative max for that one. Now let's take negative 1, 0. When you take negative 1, 0, what do you get for D? You substitute in negative 1, 0 into our formula here. And what do you get for D there?
Negative 4 over e to the 4/3.
Wow. Negative 4e to the negative 4/3.
No,
No.
4 over e to the 4/3. Oh, yeah, well, yeah.
Okay. Is that going to be positive or negative here?
Negative exponent.
Okay, that would be a negative. Okay. So, it's a negative. The point is, it's less than 0. When D is less than 0, what do we get? That's a saddle point. Saddle point at D less than 0. This conforms totally to what the graph gave us. A relative max at 1.10 and the relative and the saddle point at negative 1, 0. That's exactly what we got. Okay?
Things at 1, 0.
Yeah, this. Okay. 1, 0. This point right here is 1, 0. This point over here is negative 1, 0. Saddle point, relative max. Exactly what you would expect. But the problem really isn't done yet. Because what we have to do is test that border, okay? That border where we have that curve. So the last thing to do would be to test the border where we have our function, but it's pretty clear cut. Our function on that border is y equals, if you do y in terms of x, e to the 2/3 minus x squared. Okay? Now, that's this graph right here, okay? That's the graph. That's the graph that's on the border, okay? Yes.
Where did you get that? Where did you get the function from? Where did you solve
I got it by letting, I set x equal to -2. And so when you put a -2 in there for x, you get -2 cubed is -8, but you have to take the opposite of it. It's 8/3 plus a -2 is 6/3. So you get -8/3 plus the 6/3 to get e to the -2/3, or e to the 2/3.
That
Hold
makes
on.
sense. That makes sense.
Okay, minus the x squared. I replaced the y with x, so I had y as a function of x. All right, it's something like that anyways. What is this value when x is equal to 0? At x equals 0, this value clearly is y equals e to the 2/3. The question is this point on that edge greater than the height of our relative max over here, our critical value? Okay? That's sometimes what you had to do back in Calc 1. You know, the critical values would give you a relative max or min, but it's possible an endpoint would give you a greater value or a less value, all right? So the thing to do is to test out the function at 1, 0. So let's go back to our function. Here's our function. I'm almost done. I'm almost there. Z equals E.
So I was testing at 0, -0.
What's that? And we're going to test 1, 0. This is where we got our relative max at 1, 0. And we want to see how this value compares to that value. Okay? Because at 1, 0, we're going to see if that mountain, okay, is greater than e to the 2/3. And it turns out you get e to the 2/3 again. So both points, okay, give you the same height of e to the 2/3. So what's the maximum value of that function over that interval? E to the 2/3. Where does it occur? Two different values. At 1, 0 here, and also at the point at the edge at -2, 0. Okay, at -2, 0. Yes?
I don't think I lost at one point, but on the left-hand side of all the equations, are those all y's or are those all z's?
Y is easy.
Oh, yeah, that's a good call. Those are y's on the top 2 and z's on the bottom 3. These are referring to just this. This is the curve at the edge. Okay, that's the curve at the edge. These are the function, that whole three-dimensional object. Okay, that's what these are. Okay, that's it. All right, so here's what you should be doing. For tomorrow, you should be doing max min problems, the last two sections of this this chapter. Tomorrow we're going to do, okay, here we go. I promise you this. Okay, we are going to do the space station problem of space in the space station. We're going to do that. Oh, I thought that was
Hopefully there's no space in the space station.
What's that?
Hopefully there's no space in the space station. That'd
Oh,
be bad.
that'd be bad?
There's space inside.
Oh, space is supposed to be outside. No, we're not. Good call. That was pretty good. All right, see you guys tomorrow. Math team, we're doing proofs. It's a big day today for proofs. Proof day. Proof, pizza and proof. What? Oh, you gotta go wash your cat? Is that it? Oh, man.
I mean, like I tried my wall. I didn't really get that.
Yeah.